So very good morning to everybody. So today we'll be discussing about the ASIC front-end design flow. What are the tools we are using in VLSI industry? So I'll be covering in basic, starting from the RTL coding. Once RTL coding is done, what are the tools we are gonna use? And finally, the correct collateral, right, will be handing off to backend team. So the basic flow is once the architecture team will write the architecture, right? So it will be handing off to micro architecture team. They will be uh, micro architect the design. Once that design is finalized, the RTL team will be writing the RTL code. Once RTL code will be written in the IP level, that will be integrated by the integration in the engineer in the SOC level. So once the SOC level RTL will be generated, then the front-end tools will come into picture. Let me go to next slide. So yeah, so this is the basically the agenda. Now, what is front-end design flows, RTL coding tools, and so on. So as I was saying that once the top level RTL will be generated, so next the quality checks tool will kick in. So first tool, once that top level RTL will be generated, the first tool will be the lean tool. So lean tool makes sure the RTL, whatever is coming from the integration team, that will be synthetically correct. So for that, in the industry, there are basically two vendors. We are using the lean tool. Okay, so we are using Synopsys tool that is called Spyglass Lint. Okay, that lean tool will make sure the RTL is following the coding rules and design guidelines. So as per our project milestone, we will be setting the rules. Basically, what are the rules we need to check? Okay, so I'll be going about few rules for each tool uh, today. So lint, as I have already explained, then once lint is done, we'll move to CDC. CDC is also a clock domain crossing when your basically a signal will be uh, traveling from one domain to another. So for that reason, we need to make sure all your data has to reach to the destination correctly. For that reason, we'll be using clock domain crossing. And next is your Fistel. So Fistel is also a tool from Synopsys, that is Synopsys Timing Constraint Manager, where we'll be making sure our RTL is aligned with the timing constraints given by the designer. So we'll make sure the RTL is synced to it constraint. Okay, so for here we will be doing the constraint lint checking. So once constraint lint checking is done, we will be doing the RTL verification. That is one of the flow, and there is one more flow in front end that is called Fistel RTL constraint promotion. So for that, we'll be promoting the IP level constraints to the partition level. So once that is also done, we can make sure that trophy still your constraint is as per sync with the RTL. So I mean the next flow will be your LEC. LEC is also called as logical equivalent checking. So here there are two vendors again. One is your conformal LEC by Cadence, and one is your Synopsys formality that is from Synopsys. So I'll be going one by one in detail later. The next flow is VCLP, which is a low power check, again coming from Synopsys. And next is your basically the synthesis tool. Synthesis is coming from Fusion Compiler. That is a tool, basically Fusion Compiler, and the company name is Synopsys. So we can use this tool Fusion Compiler to make sure that our RTL is synthesizable. It means your RTL is converted to gate level netlist. And there is one more tool called Formal. formal verification, where we'll be checking your the RTL. There will be many modules in the integration, right? I mean the top level RTL, where the modules top module is connected to some modules correctly or not. We mean we can check as per the depth or how much depth we are giving. This tool can go from top level to sub block 1, sub block 2, and so on. We can check the connectivity of clock, reset, whatever we can mention in the TCL file. It can do the connection checking. Okay, so these all tools mostly in all the industries, I mean in all the companies, these tools are used. Okay, so we'll be discussing one by one with few rules now. Okay, so let's start with lint. So as I already mentioned, lint is a tool which is used for checking where the RTL is following the design rule and coding guidelines. So it will check many rules, but we can set as per our configuration, whatever configuration and what milestone we are setting. In that milestone we can set the rules. So the most common rules which I'm going to discuss now, number one is your inferred latches. Okay, next is your combinational loops and multi-driven nets, with mismatch, bit overflow, dot flow, and we should not use combinational statement in I mean blocking statement in sequential, and non-blocking statement in combinational. So these are the rules which we are gonna check in lint. So as I mentioned, the first rule is your inferred latches. So inferred latches mean if you are writing some case or if else statement. So if you have written if and else is missed in your code, so tool will mention that latch is inferred in the design. And tool will give a error that okay, latch is inferred, we need to fix the violation, we need to open the RTL code, we need to check through schematic whether in which part of the code is latch is inferred, and accordingly we can fix the code. Second is your one more condition will be in inferred latches is you have not mentioned the full case basically. So in case statement you have mentioned suppose 2-bit select line you have taken, and out of 4 condition you have mentioned 3 condition. So in that case also tool will infer latches. Either you have to write all the cases, or if you are mentioning 3 case or 3 condition using case statement, then you need to write default also. Then in that case tool will not infer latch issue. Okay, and next is your multi-driven net issue. In multi-driven net issue, when uh, multiple driver, or you can say multiple I mean different input is assigned to same output, so in that case tool will tell okay, there is a multi-driver issue. In that case also we need to make sure which input should drive to that output, basically that you need to see, you need to fix in the design. Okay, and the next violation will be, as I already said, in sequential statement we should not use combinational, right? And in or blocking statement, we should always write blocking statement in combinational block and non-blocking statement in sequential block. If you are not following that coding guidelines, that tool will throw issue. Okay, and next is your the most we are getting often in our project will be your bit width mismatch, where you'll be assigning a 3-bit signal to 2-bit, right? So or 4-bit to 3-bit. So in that case you are not assigning complete signal to output, right? So in that case tool will tell that okay, this is a bit width mismatch issue, your data will be lost in that case, right? So those are actually flagged by lint. Even though there are a lot other rules that we cannot, that we can see as we can set as per our milestone. Okay, so next flow is CDC. In CDC, it's a clock domain crossing where we are making sure when the data is traveling in asynchronous clock domain, it has to transfer correctly. I mean, right? Data should not be lost, because in SOC there are multiple blocks in the design, multiple blocks has different intention in the SOC, and that clock is different because there are some timing blocks, some gaming blocks, or calling block or music block. There are different blocks in the SOC, right? So every block has different speed, right? So, and that is obviously intentional. For gaming and all, you want fast, or for calling or any the block which you are not going to use, that will be little most often that will be less clock. Basically, that is a hypothetical example I am giving. So in that case, whenever a data is traveling from one domain to another, we need to make sure the data has to pass to other domain correctly. So there are many synchronizing I mean techniques we have used. Few synchronizing technique I will be going to explain today. The first, let us segregate these two into two different I mean technique. One is a single bit synchronizer, one is multi-bit synchronizer. Even in single bit synchronizer, there are different technique. If you see in single bit synchronizer, we have two flop synchronizer, three flop synchronizer, toggle synchronizer for the pulse, okay, handshake based synchronizer, and so on. Okay, and for multi-bits, we have many synchronization technique. Few we are gonna discuss today. First one is your most often is FIFO synchronizer. Then we have gray code encoding synchronizer, multi-bit synchronizer, max recirculation technique. So those synchronizers we are going to use to synchronize multi-bit data from one domain to another, right? So let us discuss about single bit synchronizer. So as I said, the first synchronizer is your two flop synchronizer, where we are using two D flip flop back to back. In the two D flip flop back to back, when a data is transferred from one domain to another, so if your data is changing in the setup or hold window of the flop, your data will be going to metastability, right? So in that case, what this two flop synchronizer will do, the first flop, when data is coming, it will go to metastability and will make sure that data will be recovered in the first flop, okay, and the first flop stable output, the second flop will sample. So in that way we are synchronizing the data going from one domain to another. In few cases, when your data is changing very fast, that time two flop synchronizer may not be sufficient. So in that case, we'll be using three flop synchronizer. Okay. So we'll be adding one more flop stage in cascade to synchronize the signal from one domain to another. This is one of the technique in single bit. Okay. And let us discuss few more technique for multi-bit. So in multi-bit synchronizer, we are having uh, I mean multi-bit synchronizer, max recirculation technique, two flop synchronizer, gray code synchronizer, and so on. So this is also for multi-bits. And mm, for FIFO synchronizer, we can use if a signal is going from fast domain to slow domain, and receiver side is not able to process or sample the data coming from fast domain. So in that case, we need to store the data in memory, and accordingly, as per the read write pointer synchronization, we can take the data out and we can receive the data in the receiver domain. So this is about CDC. Next, we'll move to Fistel. In Fistel, as I already said, it's a timing constraint manager tool where we'll be making sure the RTL is sync with the constraints. For that, in industry, mostly in the front end, we are using two flows. One is your RTL constraint promotion flow. Second is your RTL verification flow. So in the constraint promotion flow, whatever the IP is delivering the constraints, we are rolling up to the partition level. If you're running constraint promotion in the partition level, so we'll be taking the constraints and we'll be taking the partition level RTL and partition level clock information, and we'll be using this tool, and we'll be setting all the input collateral as per the config, and we need to make sure your constraint promotion is done correctly. So in that case also, while doing this, we'll be facing some issues like it's a setup issues if you are using some constraint in there, some design objects like clock or any design object or port, right? Whatever you are mentioning in a constraint that is not present in the design, then tool will check that okay, this port is not present in the RTL. So we need to make sure setup wise these constraints should match with the RTL, then only tool can do the promotion correctly. This is one of the flow I mentioned for Fistel. Next is your RTL verification flow. In RTL verification flow, so here what we have to do is first thing is setup wise it should be clean. I mean the constraints is correct. It should be correct as per the RTL. The clock, the RTL port information, everything. So whatever is mentioned in the constraint should match with the RTL. Then only setup wise we can claim to be correct. Once setup is clean for the RTL verification flow, we have to go to false path multi-cycle path verification and generator clock verification. Okay. So what I mean as far false path verification is, false path are those path which architecturally we can claim that from this path the data will not propagate from source to destination, or the path will never be sensitized in the design. So those paths are called as false path. And if tool is claiming that okay, this path is not really false by the tool, we need to make sure, we need to debug why this path is not false path. We need to debug and we need to talk to the designer that these are the path which tool is claiming as not false, and this is the reason. We need to make sure. If the designer is telling that okay, this is uh, expected by design construction and all, then uh, we can waive it as per designer confirmation. And next is your multi-cycle part. Multi-cycle part where uh, it is expected that a data is traveling from source to destination in more than one clock cycle. So in that case, we will be telling to the tool, okay, this is the path where data will take at least more than one clock cycle to travel to the destination. Okay, and in that case, normally the expectation is data has to travel from one domain to another in one clock cycle. So that is why these are called exceptions. We are giving exception to few parts. Okay. So again, if tool is not able to apply multi-cycle path for some reason, we need to debug those, and accordingly we need to talk to the designer and we need to fix this. Okay, this is brief about the Fistel. And next is your LEC. So LEC is a logical equivalent checking where we'll be checking the RTL, right, is correct or not. I mean, the RTL has to go through many cycle, starting from RTL design. It has to go through lint, CDC, fishtail, synthesis. Finally, it has to go to backend flows, and later mm, it will go for fabrication, right? So in these many phases, the design which you have signed off, or the design which designer has made, that should not change. If it is changing, right, our intention will not be proper. The design should be correct as per the specification. So we can check through this LEC tool where the design which we have decided should be correct till end. So in that case, we are again using two flavors of LEC. One is your FEV light, that is called formal equivalence verification lighter version, and one is called sim to sim. So in FEV light, we are just checking the RTL is tool is going to read RTL correctly or not. If there is any undriven, if those are there, we'll be going to clean those in FEV light. Once FEV light is clean, it is better to proceed for sim to sim. Sim to sim means your synthesis versus simulation, where we are telling that the simulation, the RTL which is going for simulation and the RTL which is going for synthesis, that's that should be same. That should not change. So we'll be giving input to the tool, the RTL, at a different flavor of RTL. And there is any heap in the design, that for that heap we'll be providing .lib, okay, and we'll be running the tool and check whether the sim to sim is correct or not, the flow is correct or not, okay. And for that also, if there is some violation, you need to debug and you need to send to the designer and need to make sure that those are correct, right? If required, again we need to explain why tool is flagging the violation. And this is about LEC. So next is your low power tool, which is called VCLP, that is from Synopsys, as I have already mentioned. So here also we'll be checking as per RTL, the low power coding will be written, right? Sometime, what I mean is, sometime as per RTL, we will be mentioning about create clock domain or create clock ports will be mentioning, or if there is some isolation to be made from one block to another or some level shifters, those things, right? If those things has to be done, because as I already said, it is a multi-voltage design, right? Or a signal can travel from one block to another in the SOC, right? So sometime we need to send signal to the design, sometime we need to the signal has to travel from on domain to off or off to on. Sometime we need to shift the voltage level, right? So everything we need to do, and that has to be explained, right? And that has to be correct. So those once this UPF will be written. UPF is a unified power intent where we'll be writing the UPF, okay, and that UPF has to be fed to this VCLP tool and need to make sure the UPF is correct. Okay. So if the UPF is not correct, again as per the RTL, this tool will throw violation. Sometime, for example, your isolation is not correct, or level shifter is missing, or power state table is not correct, or power state is duplicate. So those things will be coming. We need to make sure, we need to debug those things, and we need to correct as per this flow. Okay. uh, and again and since these are the sign of flows, if these flows we can correct our design, we will be making sure this design will be correct in the silicon. Basically, when it will go for fabrication, definitely chip will be made. So that's why we need to make sure through the sign of tool our design should be correct. Okay. So next will be your synthesis will be done by fusion compiler. And even though there are many tools like Janus from Cadence, through this we can do synthesis. So in our company we'll be using fusion compiler, so where we'll be making sure your RTL is will be converted to gate level netlist. Okay, so here again the input will be your RTL, your timing constraints that is coming from designer, and if there is any heap in the design, for that we'll be using .libs. And if there are some standard cells we are gonna use, like your AND gate or OR gate, or some memories, right? Like what I mean as FIFO and all, right? So in that case, we'll be using some standard cell, and that we can directly instantiate in the design, because as this is standard cell, we don't have to write in the code. We can directly instantiate in our code. So those will be our input for the tool. And once this setup is done, we'll be going to run this tool fusion compiler, and we will convert our RTL to gate level netlist. Okay. So these are all other tools, mostly in all our the front end uh, flows. I mean the front end teams are using in all the companies, and we'll be making sure the get level netlist will be handing off to backend team. Okay, and in the backend again they will be using in their flows, they will be running and they will be running, I mean, mm, for example, the different netlist will be generated using Fusion compiler tool and other tools, and they'll make sure the design is correct. Then finally your design will be going to foundry. So these are all the flows today I discussed. Okay, so next we'll be going to RTL coding tools. So RTL coding tools, as I mentioned here, while doing RTL coding we need to put your RTL in some file, right? And that file we can open through this Vim editor or Emac. In this way we can open our file through Vim editor. Why we are using Vim or Emac, right? This is a open source, and this is we can edit the file, or we can do any, I mean, anything. Sometimes we have to delete the line, sometimes we need to add some extra line in the code. Through this Vim we can easily play around the file as per our need. So this Vim editor is important and it is used by our industry. Next is your Verdi. Verdi is a tool which is used for debug. Sometimes we need to open the waveform where we will be debugging what violation in which portion it is coming, right? We can traverse back, we can check the driver, we can check the load, how to do easily, right? So this Verdi is very handy tool. Okay, from the associate, right? As I said, our integrated RTL will be consist of IPs, partition, tile, minuting, right? So if you open a Verdi at the associate level, we can go down. I mean, from associate, we can go to partition, we can go to IP, and we can check the RTL, we can add the load, right? I mean, we can check the driver, we can check the load, and you can debug the violation easily. Apart from that, we can check the schematic also, where you can add the port information, NAT information, clock information, everything we can add there, and accordingly we can debug that. Okay, so these are the few tools we are often use. Okay, so next slide will be moving. So this is the simulation tool we are using in the front end. So first is VCS, QuestaSim, Exilium, and so on. So VCS is come again from Synopsys, where we are making sure it is used for compilation and simulation. So basically we are feeding the RTL to VCS, and if there is any issue while compilation tool will flag those violation, we need to I mean, debug those violation. We need to make sure through VCS this is uh, compilation clean, and we can again simulation as per test bench. We can check the waveform. We can debug your RTL, right? Okay. So next slide is about debug and waveform tools. So there are few tools which are most often used. The Verdi is from Synopsys. I have already mentioned about Verdi. You can check about SimVision, QuestaGui. Those are also the most often used industry tools for debugging, to check the load, to check the drivers, waveform, and so on. Next is about lint tools. This I have already explained. This is the most common used industry tools: Spyglass lint, Ascent lint, HL lint, and as I've already again discussed about lattice, unused signal, unriven, and so on. And one thing I like to add again here, in lean tools, as per industry also there are some other tools which company to company they are using, even that is not available in the market, but those are same only. Only the thing is the rules will be different, or rule will be some new rules they will be adding. That's it. But the way of debugging and most common rules will be same across the tools. Okay, you don't need to worry for lint. Not only for lint, there are other tools which I explained. There also maybe for some company they will be using some in-house tools. Okay, so next will be your CDCRTC. Again, this I have already explained, but just I mentioned about the tools. You can see this is I mean, from Synopsys we have Spyglass CTC, Questa CTC, Jasper CTC. Is depend on different vendors what they are naming them, but the way of debugging and the rules will be most commonly same. Okay, and this metastability means, as I already mentioned, when the signal is going from one domain to another, the first flop will go to metastability, because the signal is coming in the setup and whole window of the first flop. That is why the signal is going to meta stability, and the second flop will sample the stable data. And here one more concept I would like to add in the meta stability, that is called your MTBF, which is called mean time between failure, where we'll be making sure there is a formula where we'll making sure the synchronous data frequency, signal frequency, and setup whole window. Through that, we'll be getting the MTBF value. In that MTBF value, we can make sure uh, how long data will be stable and after what time your data, the flip flop will fail. So from meta stability value only, we'll make sure when your flip flop will fail. So next, will be about synthesis tool. So synthesis tool are design compiler, Jena, COCs, right? And your RTL will be converted to gate level netlist by this synthesis tool, right? And next is your formal verification tool. In formal verification, there are tools from these vendors. Jasper Gold from Cadence, BC from Pablo Synopsys, right? Questa Formal, and so on. So here there are many flavors in Formal. One flavor which I explain is your connectivity checking, where we'll be checking from your top level to submodule 1, submodule 2, what are the connection available, for example, clock, reset, right? Or any ports, right? Input, output, in, out, right? If you're checking, if you want to check, right? From top level, your input is connected to top block level 1, block level 2, and on, right? If those are correctly connected or not, to this formal verification tool, we can check. Similarly for clock, reset, and so on. And in other flavor we can do from formal verification is like assertion based formal verification, where we'll be telling that assertion wise your design is correct. Normally through RTL verification, right? The guys which are doing verification, in verification cannot catch all the bugs, right? It is not possible to write cases for all the bugs, all the corner cases. For that reason, this formal verification tool is handy, where it will check statically, static method it will apply, where you can make sure your design is check infinity minus one scope. We cannot claim that it has covered all the possible scenarios, but we can definitely claim it will go to infinity minus one case based verification it is doing. So for that also, this is very handy tool for the verification guys, right? So we'll be going to next slide. So here, let's discuss about a summary what we have discussed today. First, we have discussed about the front end flow, how the RTL is traveling from front end to the front end RTL to front end flows, and finally to back end. What are the tools we are going to use, and what tools are available in the market? What are the rules we are checking in all the front end flows? Even though I might have missed something, you can directly ask me in the comment section. So I'll try to cover those, and whatever I have explained, those most often rules I have explained. Okay, and yeah, that's it. That's all from my side from today. Thank you, guys. Thank you for listening. Bye bye.